In this video, we're going to look at how to assign R and S configurations to chiral centers. R and S configurations are basically a way for us to tell how our molecule is oriented. So if we look at this first example here, we have 2-butanol. It's butane with an OH group coming out on a wedge. The way we're going to assign R and S is by looking at the 3 groups that have the highest priority. What do I mean by that? We're going to look for our chiral carbon first, so in this case it's going to be right here. And from there, we're going to look at all the different atoms that it's attached to, and we are going to assign priority based off of that. Our chiral carbon here, we have our OH on a wedge, so that means we actually have a hydrogen on a dash that's just not shown. This chiral carbon is directly connected to one carbon here, and an oxygen here, and then we also have our hydrogen. To rank by priority, we're just going to look at their atomic number. The larger the atomic number, the higher priority. So in this case, our oxygen on the wedge is going to have the highest priority. It's going to be number 1. The hydrogen has the atomic number 1. That's going to be the lowest. So we know that's priority number 4. So now we just have to compare the priorities of the 2 other carbons that our chiral center is bonded to. We're going to look at what those 2 carbons are bonded to. The carbon on the left is bonded to 3 hydrogens. The carbon on the right is bonded to 1 carbon and 2 hydrogens. Overall, we can basically eliminate these 2 hydrogens because they're the same for both of them, and we'll be comparing a hydrogen to a carbon. The carbon's going to win because it has the higher atomic number, so our alkyl group on the right is going to get 2nd priority, and then we have 3rd priority on the right. The reason we did this is because we want to know what the top 3 most prioritized groups are. Hydrogen's going to be last, it's number 4, that's the one that we don't have to worry about. If you have a hydrogen, you know you're going to want to send that one to the back. So if you can orient it as to where the hydrogen is going to be in the back and our first group is going to be in the front, that's great. If we don't have our first group in the front, you may have to practice your spatial awareness to try to imagine what this molecule would look like from a different perspective so that the hydrogen can be on the back. But now looking at these 3 most prioritized groups, to assign R and S, we want to look at the direction of the prioritized groups. We want to see if we're going to go clockwise or counterclockwise as our prioritized groups are decreasing. If we start here at our first group, we're going this way clockwise to get to our second group, and we continue to go clockwise to get to our third group. If we go clockwise, we're going to end up with the R configuration. If we go counterclockwise, we're going to end up with the S configuration. If we look at another example, right underneath it, it's 2-chlorobutane. Essentially the same thing, just instead of the alcohol group, we have a chlorine. But this chlorine is on a dash instead of a wedge. And that means that we're going to have a hydrogen that's on the wedge. Well, we know if we have a hydrogen, that's going to be the lowest prioritized group. We already know this is a 4. Our chlorine is going to be the 1. And then based off of what we did last time, we know that this is going to be 2. And this is going to be 3. But how do we assign R and S if our number 1 priority is in the back and our number 4 priority is in the front? Well, we're going to do the exact same thing first. We're going to start at our number 1, and we need to go clockwise to get to number 2, and then clockwise to get to number 3. We would have in our configuration if we just go off of the fact that we went clockwise. But since this whole structure is inverted, our number 1's in the back, our number 4's in the front, we also have to invert our configuration. So even though we went clockwise, which should be R, this is going to be the S configuration. Let's look at the top right example. This is 3-bromopentane. If we identify our chiral center, the only place it can be is here in the center. But we have an ethyl group on the right and an ethyl group on the left. So this is not a chiral carbon, meaning that we can't assign R and S to this because there's not 4 unique groups attached to that carbon. This will not have R or S. But the bottom right one, though, will have R and S. We have another chiral carbon here, and we actually have a second chiral carbon right here. You may notice that the one that has the alcohol group does not have a wedge or dash, which sometimes it might be written that way, which is why that part's written there now. And we're going to go over how to do it, but it's going to be the exact same thing. First, let's look at our third carbon. We have a bromine group attachment, and then we know our hydrogen is going to be in the back, which is perfect. And then we have those 2 ethyl groups, but now we have some substituents. We're going to do the same thing that we did before. We're going to compare the 2 atoms that chiral carbon is bonded to. Well, they're both carbons. We're going to move on to the next part, where we see what those carbons are bonded to. On the right, that carbon is attached to an oxygen, another carbon, and a hydrogen. Whereas the carbon on the left is trigonal planar. This is going to be an sp2 hybridized carbon, and it's only attached to 2 other things. It's attached to a carbon, and then it has a double bond to oxygen. When we have double bonds, we're going to write as if it's bonded to that atom 2 times. With that double bond, we're going to say we're attached to oxygen 2 times. Now, if we compare, we can rule out the carbon. These 2 oxygens are going to have a higher priority than the oxygen and the hydrogen when we eliminate even further. Meaning that our substituent to the left is going to be priority number 2. Our hydrogens in the back, we know that's number 4. And our other substituent on the right is going to be number 3. When we look at our direction, we're starting at number 1. And as we go to 2 and then to 3, we're going clockwise. This is going to be the R configuration. And to denote that, we're going to put a 3 for carbon 3. And then for carbon 4, which is the one with the oxygen, let's see what that would be. When it's written like this for our chiral center here, and we don't see any wedges or dashes, we're just going to look at the direction. If we look at this chiral carbon, it's bonded to a carbon, and an oxygen. That oxygen, once again, is going to be the highest priority. After that, we can tell that this super long chain is going to be the second priority, and then the methyl is going to be the third priority, with our hydrogen being the fourth. That's not shown. To get from 1 to 2 to 3, now we're going counterclockwise. Counterclockwise is the S configuration, meaning that this center is going to be a 4s. This molecule is going to be 3r4s. Let's look at one more example, this one being a Fischer projection. The first thing we need to do is identify what all of our chiral carbons are. Usually when we write our Fischer projections, these 2 terminal carbons are not going to show exactly what they are, but since we have 2 oxygens and a hydrogen attached to the carbon, we know that they're going to be carboxylic acids. That being said, that means that the carbon-oxygen has a double bond, meaning it can't have 4 substituents, so those 2 ends are already ruled out. If we look at this carbon, we're attached to this longer carbon chain, the carboxylic acid, the alcohol, and the hydrogen. That is a chiral center. If we look at the bottom carbon, that's attached to the exact same groups, just reversed. But if we look at the carbon in the middle, this one here that's outlined in purple, is this a chiral center? It's not, because it's bound to the alcohol and the hydrogen. Those are 2 different groups. But this group and this group are the exact same thing, meaning that we don't have 4 unique substituents on that carbon. We're only going to have 2 chiral centers on this molecule. Let's look at the top one first. If we look at what this carbon is bonded to, it's going to be a hydrogen, an oxygen, a carbon, and a carbon. We know that that oxygen is going to get the priority. We'll put a 1 there. We know the hydrogen is last. We'll put a 4 priority. Now, when we compare these two carbons, we're going to have to see what they're bonded to. The carbon on the top has a single bond to oxygen, and then it has a double bond to oxygen. Meaning there's 3 oxygen attachments is how we're going to write it. The carbon underneath it, which is this one right here, is attached to an oxygen, hydrogen, and another carbon. The fact that we're attached to another carbon and hydrogen is already telling me that the top is going to be a higher priority. So we can assign it as 2 and then 3. Now we're going to ignore 4 here, and we're going to look at the direction that we're going in. So we're starting at 1, and we go 2 and 3. We're going counterclockwise, giving us the S configuration. This is going to be carbon 2 is going to be the S. Let's look at carbon 4. It's going to be relatively similar because we're looking at a symmetric molecule. Our first attachment is oxygen, carbon, hydrogen, carbon. That oxygen is going to get first priority. The hydrogen is going to get 4th. And comparing those 2 carbon substituents that we have, we already established the other way that the carbon on the bottom, the one that's part of the carboxylic acid, has a higher priority. That one's going to get the 2, and the other carbon chain is going to get the 3. If you look at the direction of our priorities, we're going from 1 to 2 to 3. We're going clockwise, meaning that this carbon number 4 is going to be the R configuration. If you found this video helpful, please consider liking and subscribing as it really helps the channel. If you want to see more content related to organic chemistry, the playlist should be on your screen now. Thank you for watching.